Okay, so we just keep going. Hopefully this is still good. All right, so if you have ka to the 0, that's basically saying k times 1, which is equal to k. And so that's what this is saying down here, is that when you have a rate concentration decreases linear with time because the rate is constant and does not slow down. That's what they're talking about on the graph. This right here, rate equals ka to the 0 equals k, rate equals k, because a times a to the 0 power is 1. Okay, so here's another graph. This is another graph to be familiar. You should be familiar with both, but this is the one that you probably see on your AP test for sure. And this one is very clear about rate because we're listing rate on the y-axis and we're looking at concentration. So if we're looking at a 0 order, here we're at the purple line again, we see that even though we're changing the concentration on the x-axis, the rate is flatlined. It stays the same. So this is basically showing us that rate is independent of concentration. And that's you could read this slide and it's going to say all of that. Okay, so we move on to the next part. So we have, and notice the rate law for a 0 order. It is rate equals k a to the 0. Remember, k was the rate constant. 0, where we have a 0 that was in before. And when n equals 0, that is a 0 order, right? So if you needed to express a 0 order, you're going to put the concentration to a 0 power, all right, for a 0 order. Very important that you understand that. All right, so we go to the next section. Okay, and this is just an example of a 0 order reaction. Let's say we have some ice in a glass tube, and we are wanting that to sublime. Does anyone know what sublime means? I know you're saying that in your head. For those of you at home watching the video, you're saying, yes, I know what sublimation is. Sublimation is when you go right from a solid to a gas, all right? And so sublimation, and if they're talking about water here, that's actually kind of maybe a bad example, but if you're talking about something like dry ice, you never see it in the liquid form, right? If you've seen dry ice, it goes right from a solid to a gas, it sublimates. And regardless of how much you have there or the concentration, it's going to sublimate at the same rate, all right? It doesn't matter about the concentration. Okay, let's go to a first order reaction. Again, now this is a red background, so we're talking about the red line here, all right? So this is first order, and in a first order reaction, n is equal to 1. So if you look at this rate, rate law that we wrote for that, k, the rate proportionality constant, a to the 1, and that's where n equals 1. So that's showing that it is a first order. And in a first order, it's directly proportional. So notice the slope of the curve for the rate, the slope of the curve will give us the rate. For a first order reaction becomes less steep or slower with time. So you see this is becoming less steep. That's because as the concentration decreases, the rate slows down. All right, it's converting from A to products at a slower pace because the concentration is decreasing over time, and that's what you're seeing. As the concentration decreases, it gets slower and slower and slower as a rate, and so it's not like a 0 order where it just keeps going the same rate. That's a little bit easier to see on this next graph. On the next graph, where we have rate as our y-axis, we can see. And this is actually using a different angle here. Now we're increasing the concentration. So we're increasing the concentration because concentration is on our x-axis now. And as we increase the concentration, we increase the rate. Do you see that? And it's directly proportional. You can see that it's a linear plot, right? It's a linear plot. Notice the rate law, k equals a to the 1. All right. You could also look at it backwards, though. As you go this direction, it goes downward, right? The rate decreases. So if you wanted to know, like, okay, how do I know? If I go to 0.2, I can see that the rate is 0.004. If I go to 0.8, I can see that the rate is 0.0012, all right? So I can see that very easily. So it increases. All right, we're going to move on from there, and we're going to go to second order. And this is the last order that we're going to talk about. You should see on your AP test 3 orders. 0, first, or second. And so in a second order reaction, n is equal to 2. So you can look at your rate law here, and its rate equals Ka to the 2. And the reason why we have a 2 there is because we're saying that this is a second order reaction. In a second order reaction, the rate of the reaction is proportional to the square of the concentration. All right. And so as we decrease the concentration, the rate slows even more so than it does when it's just directly proportional. All right. And what we're doing, and that's kind of going to this point, we're comparing the red, which is directly proportional to the square of the concentration of the reactant. Okay, so again, this next graph shows this a little bit better. So, but it's also showing it in a different direction. We see rate is equal to Ka squared. We see the concentration is increasing, but now we see this J-shaped curve. And anytime you see a J-shaped curve, you should know that that is exponential. All right. You should, I don't know if you know that from math, but that is showing an exponential plot. And so that's why you see Ka squared. You should also remember a J-shaped curve from biology when you're studying ecology and populations. We show growth is in a J-shaped curve, and then it can turn into an S where it flats line at the carrying capacity, but that has nothing to do with reaction rates. Okay, although there's some similarities there. Okay, so we got to determine the order of a reaction, and it can only be determined by, look at that, an experiment. All right, now, I was going to say I don't know if we have the tools. I know we don't have the tools to do an experiment for the method of initial rates. We can do some experiments centered around rates, but not the method of initial rates. Like we're about to go over. So we're going to just have to know how to interpret data. So in this method of initial rates, you're looking at the rate for a short period of time, and it is measured by running the reaction several times with several different concentrations. And this will help you determine the effective concentration on rate. And actually, if you don't change the concentration, then you can't tell what the order of the reaction is. And we'll see that here as we move forward. So the next section here is we have determining the order of a reaction. And here is some data. Here they ran the reaction several times, 3 times if we're looking at this in particular, and each time they changed the concentration. So this is the same reaction we were looking at the beginning of the slide, A to product. So that's why we're only looking at one reactant, and that's A. And so if we look, when we took the measurement at 0.10, at a concentration of 0.10, we noticed that the rate was 0.015. And if that was all the data we have, we cannot tell what order this is. But we have more data than that because we ran the experiment 3 times. And so we can look at the next experiment, and we notice that we went from 0.1 to 0.2, right? And you would say, what does that mean? Well, what is the factor by which we changed? What is the factor by which we changed the concentration? Anyone know? We went from 0.1 to 0.2. You would say we did what? We doubled it. We changed it by a factor of 2, right? So we doubled it. And what happened to the rate when we doubled it? It doubled. And so then we'd have to find a rate law that is consistent with when we double the concentration, that the rate also doubles. All right. And so what we're seeing from this data is that the concentration, the change in concentration is directly proportional to the change in the rate, right? And so if we go back just a little bit, we will see that is exactly what a first order reaction is. The rate of the reaction is directly proportional to the concentration of the reactant. So when we double the concentration, we double the rate. Do you see that? When we triple the concentration, we triple the rate. When we quadruple the concentration, we quadruple the rate. And so it's very easy to say. So we're just using our definition of a first order to determine that this is a first order reaction. So you can also see this in the second to third experiment. We go from 0.2 to 0.4, the concentration doubled, what happens? This doubled, right? You can look at it from 0.1 to 0.4. If you go from 0.1 to 0.4, that changes by a factor of 4. And then if you look at your initial rate, it goes from 0.15 to 0.06, which is a factor of 4. All right. So you can see this multiple ways. All right, let's look at, let's see here. Okay, then if we wanted to write the rate law for this, all right, because we've determined that it is, the concentration is, the rate is directly proportional to the concentration, our rate law would be Ka to the 1, all right, because we said this is first order. And so that's all you would do there. Let's look at another one. Let's look at another one. That is the same one. I don't know anyway, read that if you want to. This one, I don't know why, but this one gives away the what order it is. Wish it didn't. I should have snipped that out when I made this. However, this is easy to tell. Look at this. We still have a change in concentration. You see this? We ran 3 experiments. We have 0.1, 0.2, 0.4. So from 0.1 to 0.2, we doubled the concentration. What happens to the rate? It stays the same. And if it stays the same, we notice that regardless of our change in concentration, the rate will remain constant. Basically, what we're seeing is that rate is independent of the concentration. That is a 0 order, all right? So what is our rate law for a 0 order reaction? Rate is equal to Ka to the 0 power. That's exactly right. I guess I did not write that in here, but that's what it should say. Rate is equal to Ka to the 0 power. Now, it is important to understand the units for K as we go from a 0 to first to second order reaction, but we're not going to focus on that at this time. But they are important to know, and you can find them very easily as well. All right, so let's look at this next one. And of course, I'm giving it away here where N is equal to 2. And so we see that when we doubled this concentration this time, that this changes by a factor of 4, right? So it's not directly proportional, it's proportional to the square. By the way, so this is doubled, so it changes by a factor of 2. This is quadrupled. What's 2 squared? 4. You see where I'm going there? And this changes by a factor of 4. So what is the factor here? And all you have to do is take 0.240 and divide it by 0.015. What are you going to get? I'll give you a second to do that, all my internet followers out there. But you should get, if you understand the concept here, and you do, I checked it. This is changed by a factor of 4. This changes by a factor of 16. All right, because 4 squared is 16. All right, and so you should see that very, very easily. Okay, now writing a rate law with more than one reactant. So far, we've only seen, and this is what this is saying, for multiple reactants. So far, we've only seen A to products, right? Now we're seeing a whole equation, and we got A plus B to C plus D, where the lowercase a is representing the coefficient, and where the uppercase A is representing the concentration. All right, or the compound, not the concentration, but the compound. So, so we're seeing how to write our rate law here. Now, as long as the reverse reaction is negligibly slow, the rate law for the proportional A to the raised power M and B. Okay, so we're not worried about the reverse reactions yet. We'll talk about that when we get into equilibrium. Someone was just being a little bit extra when they wrote that in there. When we were looking at the rate law for multiple reactions, what you have to do is you're going to have to use your method of initial rates to determine your rate law for A and to determine your rate law for B. And so what you do is you would say, okay, if A is first order, then I would put Ka to the 1. If B was second order, then I would put Ka1B squared. And then what I would do for the overall order is add M plus N, or 1 plus 2, and I would say that is a third order reaction. Do you see that? Or if A was 1 and B was 1, the overall reaction would be 1 plus 1, which is second order. All right. And so there's several scenarios there that we can look at. So here we look at this one here, and I put the answer, I guess, right there on the slide, whatever. So the example reaction, the reaction between hydrogen and iodine has been experimentally determined to be first order with respect to hydrogen and first order with respect to iodine. So here I'm telling you that they're first order. So here's the rate rate law. So K is H2 to the 1. And I'm telling you, I'm giving you that information that it's first order. So I put KH2 to the 1, but it's also first order with I2. And so that's 1. So what is the overall rate law, or what is the overall order? It is 1 plus 1, or second order. Do we see how we're getting that? And so that's all there is to that. Not much to it, but there is something to it. Huh. I wonder why I got a superscripted 2 there. That's not right. That should be a subscripted 2. Oh well, somebody messed up when they did a superscript instead of a subscript. Okay, let's look at this one, even though I give you the answer, right? The reaction between hydrogen and nitrogen monoxide has been experimentally determined to be first order with respect to hydrogen. So once again, it's KH2 to the 1 because it's first order to hydrogen, and second order with respect to nitrogen monoxide. So NO2. So this is where we're getting this from. It's NO first order with hydrogen, second order with NO2. Overall, it's 1 plus 2, or third order. Have we talked about a third order? No, we sure haven't. But can you tell me if it's a third order reaction or not? Yes. Okay, so we're not going to go over multiple orders other than 0, first, and second. But if they ask you to add, you can say that's a third order. Do you see that? Even though you've never heard of a third order and we haven't gone over it. That's how you get there. Okay, now determining the order and rate constant of a reaction, and we're putting it all together. Now, this becomes a little bit scary. Scary, scary, scary. So I'm going to have to go in between my OneNote and this here in the next little bit. So what you're going to do, and you need a calculator. So go to desmos.com if you need to, but get you a scientific calculator, and you're going to need to be looking at this real quick. So it's telling us that it's almost time for lunch. Okay, no, it's telling us the initial rate of the reaction is measured at several different concentrations of the reactants with accompanied results from the data, and I want you to determine the rate law. Okay, so when we're using a rate law, in our rate laws, we only express our rate laws in terms of reactants. Only in terms of reactants. So what we could do, and let me get this where we can see this in another light. And I should have probably had this already there, but I don't. Let me get this where we can see this in another light. Let me snip that real quick so we can see this whole slide, and we'll go over this real quick. Okay, whoop, I don't want you to see that. I went to the next slide. Okay, determine the rate law. There we go. And let's go to a OneNote so we can write. And I'll show you this because I can't write in a PowerPoint. That's all there's to it. Okay, so let's go to a new one. All right, and here we are. So when we look at this, we need to determine the rate law. We can go ahead and write a generic rate law. All right, and what I mean by that is we can say our rate law is rate is equal to K, and with this is only regarding the reactants, NO2, and you can say M, we don't know what it is, and CO, N, right? We don't know what they are. We're going to fill in what is M and what is N after we use the method of initial rates. Does that make sense? Okay, so first let's determine what is the order for NO2. What is the order for NO2? Okay, so order for NO2. We're going to look at that first. So what we have to do is we have to find a place on our chart, where we are only looking at a change in NO2, but that CO stays the same. So if you notice, there's all kinds of changes in NO2. Like we would not want to go here. We would not want to compare there. Why? The concentration stays the same. So we have to compare 2 points where it changes. So we can see that it changes here, here, and here, right? And we can also see that it goes from, it changes here and here. All right, we can do that. So, but notice this. When we change at this section, all right, when we change at this section, 0.2 to 0.4, this also changes. So any changes in the rate could be as a result of CO and not just NO2. Do you see that? So we can't use that point because it will not work. But if we look here, this stays the same, right? And the only change that is made is to NO2, all right? So the rate change here is only as a result of NO2. So I have to use these 2 points, all right? I have to use these 2 points. And I'm not bound by just using those 2 points because there's other places where I can use this too, but that's a good place to start. For instance, I could also use these 2 points. I could use this one and this one. Why? Because in both of those, what happened to the concentration of CO? Stays the same. Do you see that? So I'm not bound by those first 2 points. I'm just going to use those because that's what I chose. All right. I could also look at the difference between 0.1 and 0.4. That's not a problem because, and only because, the concentration of CO is the same, right? I could not use this point, right? Because now, even though NO2 doubles, the concentration of CO also doubled, right? So I would not be able to use that point. That would not work. So we are going to use, just for this trial here, and we'd come up with the same answer either way. We're going to use these 2 points, all right? And so that stays the same, and we're going to be looking at these rates. All right, so we don't need to consider CO at all because there's no change in concentration. So what you want to first do is determine by what factor is the change of concentration. Factor of change, that's what that triangle means, in concentration of NO2. And so what you're going to do is you're going to take your higher value. Ideally, this would have experiment numbers, but they don't. So my higher value is 0.20 molar, and I'm going to divide that by 0.10 molar. And what you should see is that you get 2. All right, so it changes by a factor of 2. Concentration changes by a factor of 2. Now, we're going to have to see factor of change in rate, right? So now, notice I'm going to keep these lines the same. If I use 0.2 as my first or my initial, in my numerator initially, I need to use it now. It's also the higher value. So you're going to see 0.0082, and you're going to divide that by 0.0021. And what do you get there? I'm giving you a chance. Desmos.com. I'm going to make sure that I'm not telling you anything wrong on a video because I can't edit this video. I have to be perfect on these. But you get something like 3.90, and which is approximately 4. All right. So what we see is if we took 2 squared, we would get 4, right? Is that true? So when the concentration doubles, the rate increases by the square of that change. Do you see that? What rate law do we have? Yeah, it's going to be second. So we're going to change M to a 2. all right, because it is second order. All right, now we'll do the same thing, but we're going to look at this for CO, all right? And we have to kind of come up to the same conclusion here. We have to find a place on NO2 where there is no change in concentration. You see where there's no place in the change in concentration of NO2. And that's between these two values, right? They both stay 0.2, but there is a change in the concentration of CO. It actually doubles, right? And then there's also rate. So let's look and see what happens here. So here, we're going to do the same thing. Now we're going to look at the order for CO. Yeah, I don't need to put concentration. Order for CO. And so what you're going to do is you're going to first figure out factor. One day I'll figure this out. Factor of the change in concentration of CO. And so you're going to take your higher value, 0.20 molar divided by 0.10 molar. And again, you would get 2. Now you're going to look at the factor of change in the concentration, and not the concentration of CO, but the rate, right? The rate of the reaction. And this is based off of CO. And so you can put in your values. Your values are 0.0083, 0.0083, and 0.0082. And that comes out to be approximately 1, right? And so when we doubled the concentration, what happened to the rate? Did it change? Changed by a factor of 1. So does that mean it changed? Look at your values if you can't figure that out. Did they really change? No, they did not change. So what is that, or what order does that tell you it is? Even though we double the concentration, the rate stays the same. It's 0 order. That's exactly right. So N we can change to a 0 order. So now, what is the overall order of the reaction? 2. It's 2 plus 0, right? So we already have the rate law written. So because we wrote a generic one with variables, right? And we plug those in. Now this can be written another way. Because remember, anytime you have something to the 0 power, what does it become? 1. So actually, this is not wrong to write it this way, but it can be expressed another way. It can be expressed as rate is equal to K NO2 squared. Is it still overall second order? Yes. And is it changing anything? No, because anything multiplied by 1 is still going to be that same value, right? And so we can see that it does not change the rate law at all right? Because all we're doing is taking out some extra work that we had to do that would, if you put it in your calculator, it would come out to be 1, right? So we don't want to waste our time. And so that's what you're looking at there. And so that's what your notes are about. Let's see, get rid of that. So I think I went over this in the notes. Let me go back to present, make sure we're on the same page. Okay, so the answer is the rate is equal to K NO2 squared. I left out the 0 order part because it was the 1, but you saw that it can be put in there. Okay, and so we did put this together already. We could do another one. I'm not going to. I'm going to let you look at this one and then also look at this assignment that I've given you here below this video. Please take a look at that. Let's try to get those right, and we'll add some more to that as we go on. But please don't forget to subscribe to my page, like and share, and I will see you in class next time. Thank you very much for watching.